Okay, so what was this about? What kind of function did we have on the right side? Do you remember what kind of function that was on the right? She said exact accumulation. And what's our goal now in the reverse process? Exact rate of change, right? And so then what will that, if we think about that's just the reverse of the process we worked on for September and October, then what will that look like? We were just going to start with exact accumulation, and it, particularly what kind of accumulation of what in this graph? Remember? Volume of? Volume of a sphere, right? And our independent variable was? What was the independent variable? Radius, right? So given the radius of a sphere, independent variable, this is the volume of the sphere, and that's that relationship. And we said, usually in the past we thought of it as an amount. Given a radius, there is this volume. Given a different radius, is a different volume. But then how could we think of this as accumulation, right? How could we think of this as an accumulation function rather than just an amount of volume function? Do you remember what we said about that? Leo, do you remember what we said about that? Okay. So if we think of more, instead of maybe more in a continuous way, yeah, so yeah, you could think of it that way, like, and so the intervals represent what? And then what, so maybe, so somebody else. How do we think of this function, not just as amount of volume for a given radius, but as accumulation of volume? Right. 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 Yeah. You add up all those volumes, right? Yeah. So yeah, as the radius, you can imagine as the radius increases, for every little increase in radius, like Leo said, like we'll change in radius, you're going to get a little bit more volume. And then if you continually do that, continually increase the radius, you can imagine your volume expanding. So you're accumulating volume as the radius grows, right? Okay. And so we've got exact accumulation of volume here. What's going to be next in the process then? So what would we do first? Remember? In moving towards exact rate of change, the first kind of milestone. Brandon, do you remember?
We have to make an approximate accumulation graph.
Right. We'd made an approximate accumulation graph, and then was that a step function, like horizontal bars? No, because that will. Why will that fail? What would happen to your rate if your accumulation was in every interval is horizontal? Yeah, if your accumulation is horizontal in every interval, then you're just going to get a rate of change of 0 in every interval. So that's not going to work. So you guys all drew. So then you do this graph, right? And this is our approximate accumulation. So what, for every interval of 0.4, you have constant rate of change now. So that purple graph is a constant rate that's achieving what? Right? So what does that constant rate achieve relative to the actual accumulation? So yeah, what does the pink line with a constant rate achieve relative to the original volume function? Yeah.
Gives an approximate of the accumulation.
Okay. And how does it do it? So how in each interval, what constant rate did we pick basically? So what constant rate did we pick in each interval? Left x. So it was the rate only dependent on left x? Okay, so f of left x would just be the volume at the left side of the interval. Is that what gives us a constant rate? So if we say the second interval here, f of left x is just going to be that volume right there, the y value of that. So that doesn't give us this constant rate. What is it that gives us that constant rate? Yeah, is it? Okay, so that's the formula, but can you kind of explain where that constant rate is coming from? Right. Right, we're going to pick off the actual volumes at the two endpoints. And then the key to that is that now in that interval, the constant rate that we get in that interval has the same change in volume as the actual change in volume. Do you see that? That's the key to this. So the fact that they have the same change in x, that's kind of trivial. But the constant rate that we're picking is the rate of change that will achieve the same change in volume for that interval. I'm trying to make this straight. So that whatever change in actual volume that you have, we're going to do the constant rate that gives you that same change in volume, right? And what do we remember what we called that? Constant rate of change that achieves the same change in y. As the original function is called, anybody? Average rate of change. So this is key because it's not like averaging test scores, right? You're not adding up a bunch of numbers and dividing by the number of them, right? So this is a different kind of use of the word average. By average rate of change, we mean the constant rate of change that's going to end up giving you the same change in your y, whatever your y quantity is, as the original function. Does that make sense? So that's really key principle there. Okay, and then so you guys came up with this. You came up with the average rate of change function, right? The function for this purple graph. Let's see that. And that was this, right? And what was the whole structure of this? Remember, this is a thing we've done over and over this semester. We said if you hadn't learned it by then, we'd learn it forever. What's the structure of this thing? Kylie, do you remember? MDX. So the accumulation is MDX. What do you guys think? Is that right? Plus y initial. You want to change now? Okay. Yeah. So this is you're right. So MDX is definitely a very important part of it, and that's the dy part. So this is our constant rate. This is our average rate right there, and then this is our dx, and then plus y initial. So yeah, y final. So when we wrote linear segments and pieces with constant rate of change, it was always in the form y final is y initial plus change in y, and change in y being by constant rate of right, our constant rate of change math of mdx. And so no different here. That's what we did. We figured out that the left side was f left x. That's y initial, and then we're gonna build up as x changes. We've got our rate, and then our change in x across that interval will be x, current value of x minus left x. Okay. And then what did we do? Then we said, all right, now we can sketch that rate function. And the rate function would just be each of those constant rates. And we said, what's that function? So what is the rate function? Yeah, we already did it, right? So we needed m for that accumulation, so it's just the part of m there. And then we said, so we've got what? So we started with exact accumulation, we got approximate accumulation, and then we got approximate rate. And so now we want to start moving towards exact rate of change. How are we doing so far? Is this a good, is this close to the exact rate of change function that we're showing now? No. And why not? What's wrong with this rate function? Yeah, Rudy. Right, that big interval is, see all the daylight between our approximate accumulation function and the actual accumulation function. That's all going to be error, right? That's all going to be error in the accumulated volume. And so our approximation is too big, right? So our approximation is too big. And what do we need? We need smaller h's. So by making h smaller, it makes the approximate accumulation better. And then what happens? Our approximate rate starts to kind of converge on something, right? So it's like it's going somewhere as we keep making h smaller and smaller. So how do we get this mystery, right? So there's kind of like this kind of end of the line when h is really super small, and we can't really tell the difference between the approximate and exact accumulation. We end up with this this rate function. It's still approximate rate, but it's kind of indistinguishable from a curve, right? Those are still a bunch of little horizontal lines, but we see this curve forming, right? It's kind of being generated. So how do we get that? How do we get that? So the idea is letting h be small. But in this, the very last thing we said was, this is not convenient for having rate functions in the form that we like a nice either quadratics or sine functions. This left x is kind of a hindrance. We can make h small and it works. We get the exact rate, but in terms of algebraically being able to generate nice functions for our exact rate function, this is not convenient. So the last thing I said was we're gonna start something new, and this is the second half of your sheet now. Any questions so far on this? Is kind of, so that's literally going backwards, doing the reverse process of what we did before when we had exact rate and we were finding exact accumulation. This is literally the exact reverse process, and it's a valuable thing, but we kind of need to tweak it from the beginning to get something more helpful in the end. Any questions? Okay, so that's what we're going to do now. So now this time, okay, so here's what we had before. So now this time, instead of having these set intervals, notice how h is set as x moves through the interval, right? So now the first interval, h is set until x gets to the next interval, and now h is set. And these change in x intervals are set. So in contrast, we're going to transition to something like this. So how is this different? If now the blue is the new thing, right? So the blue is the new thing. How is that different? What do you observe? How about somebody new? Karen, any ideas? So what's different now about this?
X will always be 0.4 out of the interval, I think.
something's different about x now, right? So what x will always be what? Yeah. Something's. What's that?
It'll always be left x.
She said it'll always be left x. I don't know what we were gonna say. Right. So like there's no need for left x anymore. See that? Because the interval will always start at the current value of x. And so this kind of negates the need for left x anymore. Okay? So when we do that, when we do it this way, are we going to get the same approximate accumulation function that we did with the purple one? What's gonna be instead? Think about this. So now we're gonna transition to this. So what's it gonna be like now in terms of approximate accumulation? Can you guess or imagine what it will be like?
Smoother curve.
A smoother curve. Andrea, what do you think?
I'm sorry, I was busy
Oh, sorry.
reading and trying to decipher. What was the question? No, that's okay. No.
The question was, so now when we talk about approximate accumulation with this, how will it be different than what we had before? So again, what we had before,
Right.
this is what the purple is our approximate accumulation from before. When we set the intervals kind of ahead of time. Now, if the interval is kind of just like the sliding interval, it goes along with the current value of x. What could we imagine for approximate accumulation now? Approximate accumulation.
Because your interval is constantly changing, in terms of its start point, I believe that it's going to be much more exact, regardless of the length of x. That start point is always
So better accuracy.
better accuracy, yes.
Better accuracy. Okay. All right. What others do you think? Rachel, any ideas?
No, I think it'll be a lot smoother because you can see how the lines are moving on it, so then it'll be more of a gradual kind of,
Okay. Smoother. Any other comments? All right. So let me look at the questions. Okay, so the first question is, will the secant line rates of change be constant rates that change above? And by secant lines, like we had these, before we had the purple, these are secant lines. And what happened, when you get to the next interval, the rate of change changes abruptly, is that right? So we had kind of three distinct rates of change, and you just have constant, and it changes abruptly. Now what about with this? Secant rates of change, constant rates, will they change abruptly or something else? Is that a hand? Or,
No.
maybe that's a scratch. That's a hand, okay.
Seems to go, it seems to go more smoothly.
Right. So this is what, were some of you imagining this?
No,
Really?
not at all. Nothing at all.
But now that I
Are you
see it,
serious?
it's like, oh, well, of
No.
course.
Yeah, so we're still going to find the average rate of change for the interval h, but that's, there's going to be, it's going to be connected to whatever the current value of x is. Right, we did that before. It's just that now it's as soon as you change x a little bit, your approximate accumulation secant line will also be different. Whereas before it only changed abruptly at the end of each interval.
I was thinking of it as a bunch of points rather than the line it produces.
Wait, what now?
I said I was thinking of it when I was trying to describe what I thought was going to happen. I was thinking it as a bunch of different points rather than the line
Okay.
it produces.
Right, so it's still an h of 0.4, and so we're
Right.
still going to use h of 0.4 to calculate the constant rate. It's just that as soon as x increases a little bit, we're going to get a different constant rate that's going to be approximating the curve. So I should point out that when we do this, we're going to, given any x, we're going to have this constant rate right here, according to this interval h. And that constant rate will be assigned to this value of x at the start, at the left side. So every x value has a constant rate associated with it. So now when you say when x is, maybe, this is what, when x is 0.5. So this will be, right now the constant rate associated with that blue line will be assigned to x of 0.5. And also say here's x is 0.67. The constant rate that's being shown now by that blue line, that's going to get assigned to the x value of 0.67. Does that make sense? So every x value gets assigned a constant rate, and that constant rate is based on an interval width of 0.4 starting at x. Okay? So for instance, 0.2. So when x is 0.2, when x is 0.2, this is the constant rate that gets assigned to x 0.2. Okay, so what I want you to do is write the function for the constant rate of change associated with that blue line. Write the function for the constant rate of change associated with that blue line. All right, Sophia, did you get it?
Yep.
Tell me.
You said it was f of x plus h minus f of x over h.
Where did that come from?
So, earlier when we were doing the approximate rate function, we had done f of left of x minus h.
Right.
But since we've now shown that we're using x as our start of every h interval,
Right.
we don't need that left of x.
Okay.
So we were able just to replace that left of x with x.
Okay, and if we didn't know anything about left of x and we were just coming to this from scratch, how would you build your formula?
You would be doing the f of x is like your starting point in the
Okay.
interval that you're talking about.
Okay.
And so to find that constant rate, you do your an f of x plus h because you're doing the 0.4. So to find the slope between that line, you do f of x plus h minus f of x divided by your change in x kind of thing. Does that make sense?
So what does that represent right there? F of x plus h minus f of x?
That's your change in y.
Change in y, right? Because we're gonna, if we're calculating rate of change, it's gonna be what? dy over dx. That's a rate of change. Yeah. Go ahead. Yeah. Yeah, I mean we started with h, right? That's what we just said. That was what our change in x would be. Okay, so now there's that function. There's that function. And so we said what for every x, whatever the x value is, the rate of change associated with that blue line is assigned to that x value. So I think they said something about 0.55, right? Yeah, there it is. So let's just test it out. So I want you to go ahead and calculate the rate of change at 0.55 using values. Don't just plug into your formula. Think about actually using values to find that rate of change for 0.55. Yeah, so x is 0.55, and I want the current average rate of change, right? The average rate of change associated with m is 0.55. yeah, so I don't want you just to blind, like, what that formula that you just wrote.
Yeah.
Just think about doing it again from scratch. Like, here's 0.55, and what with this 0.4, calculate the rate of change. Instead of just like, here's my formula, this number goes here, this number goes here. Does that make sense?
I was starting, because you said you wanted actual values.
Yeah, right.
So I was just, so that, so there's like y, final minus y initial.
Okay.
Right? And our h is 0.
So H is 0.4, okay.
So that was where,
How are we going to get these actual values?
huh?
How are we going to get these actual values? Okay, so we got, that gives us what? Okay. So we're good with the x. How about the actual values of the y? Probably. Okay. What else? Yeah, Brittany.
0.55 is 0.75.
How'd you get that?
I actually looked at the thing.
Yes.
Or
You looked at your calculator though.
Oh, huh?
Well, you grabbed your calculator, then you said you looked. You just pulled it off the. So we need the actual. We need the values of y. Where are we gonna get those values of y? Okay. So what's the value? How do we get the value? That's a representative. It's true. I want to get this. I want to get this. I want to get this number. This rate of change when x is 0.55. Okay. Always the process. Never just the final answer. Always the process. Leo. No, I'm looking for actual values. I want to know what the rate of change is. Yeah.
So for f of 0.95, you've given us the original function f of x equals 4/3 pi x cubed.
Because.
You're saying f of 0.95, you substitute 0.95 in where you see x, so then you get about like 3.59.
And what's that all about? You set a formula and you plug in x and you get a number. What's that all about?
You plug in when the radius is 0.95.
Radius, right?
Of the sphere when the radius is 0.95.
That's right. Right.
Subtract it
Right.
from when the radius is 0.95.
These y values are volumes of spheres, right? And these two endpoints of our interval are radiuses of spheres, right? Radii. So for each of those radii, we get a volume. So what's the volume here? Someone got it? No. 0.696. Okay. And that is the radius of the sphere? Volume of the sphere. Okay, what over here?
That's 3.59.
3.59? Okay. And so to get the rate of change, so this is what that formula that you wrote is doing, right? So this is what that formula is doing. It's finding a change in volume by using 4/3 pi r cubed for the change of x of 0.4. Anybody got it? Does anybody have? Yeah. Does anybody have it then? Over 0.4. 7.43. Someone else have that? 7.23. And what's the meaning of that number? Who can interpret that? Andrea.
It's the change in volume when the radius changes from 0.5 to 0.9, or 0.55 to 0.9.
That's amount of change in volume. Agree? What's that?
No, that's the volume, that's the rate at which it changes at, sorry.
Okay. All right. So it's the rate of change.
Yes.
It's the rate of change, which means take a walk down memory lane here. Which means if it's a rate of change 7.23. Leo, go ahead. And actually, along here, given any change in x, right? So given any change in x in this, the current interval, call it dx. What can we say? Given any change in x, dx in the current interval?
The change in volume will be 7.23 times that change.
That's right.
in X.
The change in volume will be 7.23 times that change in x. That's right, in that given thing. Okay, so then we come over here, and we see this graph then. Put a red dot on there. What does this point mean then? Relative to everything we just did. Oh, that kind of changes that over there, so I gotta keep it there. So that red point, what does that have to do with what we're talking about? Noel. Okay. So what is the rate of change? So right, so in the rate of change graph, so we have the same x, but now in the rate of change graph, this y value, what is this rate of change from this interval of 0.4 over here, right? So let's just make sure that that. Oh no. What happened? Okay, we're back. So is that what you guys, can you read that? Does it say the right thing right there? 7.32. Oh, well, so there's a little bit more because the x is 0.55. Okay. So this x is for 0.555, and so then it's 7.32. So it looks like our calculation is correct. Yeah. Well, it's correct. I think it's correct. Okay. So then we've got our rate of change function, right? This rate of change function, exact or approximate rate of change? This rate of change function, exact or approximate rate of change? The $1 million question today. Yes.
I believe it's approximate.
She says approximate. They're saying approximate.
Exact.
One exact. What do you guys say? Leo says approximate. Okay.
We called the last one exact. It's way worse than this.
Okay. So, but rather than comparing it to the previous example, based on the mathematics that we're doing, why can you make an argument for it being exact, or does everyone think it's approximate? What do you think, Rachel? Not sure.
Well, I think it's approximate because it's still taking the interval with h, and even though it's a little closer to the exact rate that we saw before, and than the other one with approximate 2, it's not really taking the whole graph into consideration.
Okay.
It's like taking the small intervals of graph, and I feel like if we changed like h to be smaller, then it could still be more exact. I'm saying is like, sure, it's closer to an exact function, but it could be more exact in a way too, I believe.
Okay. And so, to think about it more exact, we want to look at the whole function.
No, not the whole function. I'm sorry. I mean like smaller bits of the function, smaller and smaller.
So let me zoom in. There. So I'm zooming in on our point. So the black curve is the actual accumulation, right? And the blue one is what we calculated. We calculated an average rate of change based on the blue one. So, and then this point, right? This point is giving us the rate of change according to the rate associated with the blue line. The function is the black one. So, approximate rate of change or exact? Or how about this? Is the rate that we calculated for the blue line, is it higher, the same, or lower than the actual rate at this x value? Do you see that it's higher? No, I'm asking you. I'm asking you. Do you see that it's higher?
Is it higher? I don't know. What part?
Around right here. So I'll zoom in again. So I zoomed in twice. So we calculated the rate based on the blue line, and the actual graph is the black one.
The rate is higher.
Right. So what we calculated was too high, right? We calculated it was too high, and that's going to be true. That's going to be true for this particular graph. That's going to always be true, right? Oh, I lost my other man. Do you see that this? Yeah. I'm just asking everyone. I'm not picking on you anymore. There we go. So for this particular situation, that secant line will always have a slightly higher rate than the actual rate at that x value. So the remedy is the same. So what do we do? So there's the rate function you guys came up with. Approximate or exact rate of change? Approximate rate of change. There's the exact rate of change. So this is where we're heading for. And it makes sense because it's all those y values are lower, right? So this exact rate of change is sitting lower than the one we have, and we can see that all our approximates are going to be too big. So what's the remedy? How do we then get from this approximate rate of change to exact rate of change? Can we make h 0? Yeah, just super small. Small enough so we can't tell the difference. So we're going to do the same thing again. So Brittany, what were you going to say? So watch, every time I make h smaller, watch the approximate, the blue one, the blue graph is a better and better, or honing in on this exact rate function. So here's h of 0.005. Yeah, question?
Even though the shape of it was correct, it was obvious that the placement was sort of off.
So, but instead of talking about placement, so mathematically what was different about it?
The values for rate of change was different.
How? So how were they different?
They were higher than we were.
Higher, right? And so we can see that in the blue line, right? The blue line is showing a higher rate than what's actually true at x.
Yeah.
Yeah, so the blue graph has higher rates than all the red ones for the same x values.
And if the blue line had been like lower, then the approximate would have been lower.
Yeah, so if we're so if this were a concave down accumulation graph, we did the same process, then all those rates would have been too low. And we would have been underneath the actual. Yeah. Okay, so then we got to take this and we got to let h get small. And that should be familiar. So when h gets small, this R2x becomes exact rate of change. So then so you could call this exact with a really small h, right? So if you said h is really small, then that is exact. Okay, then that is exact. If h is not small, then that's approximate. Okay, and so what's the key idea behind this rate function? So you all know this as the derivative, right? The rate change function. But now what's the key idea behind the rate function. That thing that I put a box around is what? Okay, more specifically? Okay, it's approximate rate of change. But specifically, what type of rate of change did we use for our approximate rate of change? Okay, and specifically, what constant rate of change? Average rate of change. Who saved us? Who was that? Good job. So it's the average rate of change that allows us to what? Build a rate of change function from accumulation function. This is the big takeaway here. And also the answering of the second question. What's the big idea about constant rate of change and average rate of change in this curriculum, right? This all these courses that you're taking. What was the big importance of constant rate of change? Yep. So what was our constant rate of change wasn't super important because it's the foundation of which part of calculus? I mean all of it, but specifically in this class, we said that constant rate of change was integral, right? Integral. You know how fast something is changing. You want to know how much of it you have, right? The forward process. Given exact rate of change, constant rate of change was the key idea that allows us to write exact accumulation, and that's an integral, right? Integral of what? M dx, right? Integral M dx. There it is, right there, dy, right? And so now here's the second question. What's the big idea about average rate of change? What's so important about that? Foundation of derivative. I know, I think it's that cool too. Right? What's the whole, why is so much emphasis on average rate of change? It's the key to, you know how much of something you have, you want to know how fast it's changing. Average rate of change, which is that's a specific constant rate of change. Average rate of change, what? Is the constant rate that gives you the same change in y as the function for the same change in x, right? It gives you the same change in y for whatever change in x you picked as your original function. But it's not a crock, right? It's not a crock. Okay, any questions? So just trying to give some context to all this emphasis on constant rate of change, average rate of change. These are the underpinnings of calculus, right? These are the underpinnings of calculus. Okay, any questions, comments? All right, so as I told you before, you have one more major GC file left. So let's get started talking about that. Unless, last questions, comments? Oh, if you want to build this file for extra credit, it would be a significant help to your grade if you achieve this. But this is hard. This is a major. This is like sand unloading, but it would be different. So let me just walk through the views. So I have actually two views. I have view 1, which is the first way, and so that's what I call view 1. And then when it's 0, it looks like this. When it's 1, it also looks like that. When it's 2 is when it shows the approximate rate being generated according to fixed intervals. View 3, or when it's equal to 3, then I put that up. That's less important, but view 3 then includes the. Did I show you how to drag and drop images? I think PC can do that. Maybe not. Maybe not. Yeah, but if you have a Mac, you can take an image file and you can just grab it and drag it onto a point line, command line, and then it'll put that image at that point rather than plotting a point. So that's all I did here was I made a math type equation as an image file, and then I just grabbed the icon from the Finder window and just dropped it on a point Anyway, I dropped it on just a point line, just a control to a point, and then instead of plotting a point, it'll put the image there. All right, then next thing, this is 4, I think. Yeah, this is 4 shows the approximate rate. 5 then shows the formula for approximate rate. 6 shows the exact rate. 7 shows just the exact rate. And then all the while, if you change h, it always works. It always gives the correct new approximate accumulation function and approximate rate function. So even that much would be worth extra credit. And then if you want to do more, you would do the whole second progression, which I call view 2. So then I show them both. That's when it's equal to 2, when it's equal to 3. Now we're fully transitioned into the new way. And then when view 2 equals 4, it shows the secant line moving with x. When that's equal to 5, it shows the approximate rate function along with line. View 6 shows the formula. View 7 puts the exact rate of change. And then again, changing h, everything works still. So now we have a smaller interval of h over here. We have a better approximate rate function until h is very small and they're essentially the same. It would definitely, if you do it well, it would definitely help, definitely boost your grade. It wouldn't be like 0.5% of your course overall. It'd be significant, right? It'd be significant to help you out. Okay, so that's extra credit and optional.
When would that be due?
Before the end of the course.
Yeah, before the end of the course. Yeah, so if you can't make those pretty like that. So that's less important. Getting the math right is more important. Okay, so that should all be on the video for you to review if you want to build that. Okay, but so if you need help, I would say let me be your source of help and nobody else. Okay, for when it comes to extra credit. You can work together on it. I just make sure it's honest effort that's your work, okay? Other questions about that? Okay, so the last project is this one. Yes, as promised. This is the last GC file. This is the last GC file that you're going to do. It's called rotations. So now this one, it's really cool and impressive, and it tends to scare students at first, but then it's not as bad as it looks. Okay, and because we're gonna lead you through the mathematics, and then once you get the hang of how to build this, it kind of like you just get over that hump, and then you run with it. Okay, so don't be too scared. But the first thing is that you have this triangle, and you have adjustable vertices. So right now P1's at 1, 2, so I could make it negative 1, 2. Right now P2's at 0, negative 1, so I could make that 0, 3. You can change the vertices and then say 2, 1. So change the triangle. And then the centers, you have this is center 1, the x and y coordinate center 1, so I can just move center 1, I can move its y coordinate. And then center 2, its x coordinate and its y coordinate, so that looks good. All right, and then here's when you change angle 1, it takes that triangle and rotates it about center 1. Okay, and then wherever you stop rotating at about center 1, here comes center 2. So from there, then center 2 rotates it from there. You're going to make that. Yes. Okay, so yeah, students, you will like it. I know it maybe looks a little scary at first, but you will like it. So that's what it does. Okay, and this is my last attempt to continue on this journey of developing a functions mentality. Okay, and I hope you'll discover on this one that using functions is the key. Okay, using functions is the key. Whenever it's convenient for you guys.
Hell yeah. Yeah.
So you guys can have time to do it, but you don't want to say it's not like December 31st or something like this, right? But it's got, some reasonable due date that's not gonna, drag it out, but give you enough time. Okay, so I'm not gonna set this in stone. You've got your projects to work on. What's that? No, this will have a due date. Okay, but we'll just decide. We have a little bit of math to do before you guys can jump into this. Okay, so we're gonna build up the mathematics behind rotation a little bit first, and then after we kind of get our feet wet into this, then we'll decide what an appropriate due date will be.
So we don't know how to do it yet, is what you're saying.
What's that?
We don't know how to do this yet.
Yeah, I would be very surprised if anyone could sit down and do this. So we're gonna. Do you have time today? Yeah. So we need to do some mathematics, just the mathematics of rotation in general. Okay, and so then like in our world of video games and animation, this is really kind of a basic thing that's used on a much higher level all the time, right? You've got an image, and then it's going to move, right? Or it's going to rotate. So this is kind of a, All right, so would you prefer, so we got about 10 minutes left. Would you prefer that we get started on the math of this, or do you want 10 minutes to work on your, so we're going to work on this Thursday, at least part of the time. Would you prefer 10 minutes in your groups, or do you just want to get started on this? Groups?
Resounding group.
Okay, I heard mostly people saying groups. So you've got 10 minutes to work on your project. If you want to consult with me, then I'm here to consult with on your project. Thursday, we'll start talking about